Hello viewers, welcome back to video tutorial on AIOS. In this video, we'll be discussing a very important concept, load testing, and load testing of a compound or ensemble of AIs, or we call it as vDAGs, which stands for Virtual Direct Data Cyclic Graphs. So we, as usual, will be using Jupyter Notebook for entire our demonstration, and this Jupyter Notebook that I'm sharing right now will be giving an overview of load testing of a vDAGs in AIOS platform. This tutorial is mainly for the users. Let's say they have some idea on connecting of multiple AI blocks or AI or non-AI blocks. If they have such ideas, then AIOS will provide a concept of a vDAG, how to connect them, how to do a load testing, how to do a scale testing. All those things will be shared in this video. And our vDAGs in AIOS platform will provide a mux kind of operation, where fan in fan out operations we call, so that is supported, as well as a sequential connection of blocks or a parallel connection of blocks. So those things are supported in AIOS. So we'll be discussing those things in detail in this video tutorial. Before getting into details, right, so I request you to watch our other videos on block scaling and load testing, where we have two videos. And in the part 1, we have taken a mid-size model, which is Magistral 23B model, how to do a load testing of a block alone. Right now, it's about not about vDAG, it's about block. So understand what strategies we took, how we calculated, how much instance to be calculated, what all metrics to be taken, policies were available, how to view the different metrics available from the model. All those were taken into consideration to strategize our scale testing. So I request users to go ahead with that video first. Then also we have second video where we took a smaller model, because when we shift the models, right, so certain concept might change. Let's say in the mid-size model, only one model was possible in one GPU because of RAM size. But when we consider a smaller model or a higher throughput model, maybe multiple models might be supported in GPU. So how to calculate again, recalculate again your number of instances or throughput. So such kind of things were dealt in these two videos. And also we were showing some load testing results, like for after running for like a few days. So you can check those videos first. Then once you watch the block scaling and load testing, right, so you have to check with some other videos like vDAGs, what is vDAGs, how vDAGs are created in AIOS. Again, we'll be discussing here, but I request user to watch these videos. So basically vDAG is nothing but virtual direct data cyclic graphs. So virtual meaning they are not hardwired, like you will create a blocks in AIOS first, and once the blocks are ready, you will create a vDAG. So you will be connecting those blocks without a hardwire. That's what virtual direct data cyclic graphs is. And they are basically for representing a complex workflows. So vDAGs can be composed of multiple AI-wise building blocks, so each responsible for a specific task or a operation. It's not just about AI, so non-AI blocks which has some task which is not a AI task, that also can be added as a part of a vDAG. So I request user to watch these videos here. Basically, in the first part, we are discussing about what is vDAG and how to construct the vDAG and what is vDAG controller. Things like that were discussed in the first video, whereas in the second video they are showing certain policies available, like say a quota management policy or a quality store policy, where in the quota management we are discussing how to bring the quota system into picture, and also in the quality store how to store and retrieve the the request and responses for your the quality policies. So quality check kind of a task we were discussing here. And in the third video, it was about health checking policy, like policy which will check the health of a vDAG by just going through all the blocks within the vDAG, whether they are healthy or not, and all things like that. And also we were discussing about the metrics. So in this, if you see the metrics here, maybe in this video lesser metrics were there, but we have added some more metrics to the vDAG, and that we'll be discussing in this video. So after watching this video, so maybe it's better to watch this video, is what I assume. So I request you to go at those videos. So let's discuss the load testing strategy. So the load in the load testing, so first we need to create an vDAG, which is like a composed of AIs or component of AIs or a ensemble of AIs. So that we need to construct. So you need to have some idea in your mind before creating a vDAG. So in our case, we created a vDAG like this, where there is one model we call the phi model. We call this as an M1 block, and there are two reviewers, R1 and R2. They are Meta Llama 3.1 billion parameter instruct model, as well as Quen 3 1.7b model. And also we have an aggregator which is a Gemma 3 1 billion model. So we have used high throughput open source LLM models for our demo here. All those high throughput open source LLM models will be deployed as a AIOS blocks here. And as you can see, there is a demux operation from M1 because the output is going to R1 and R2, and there is a mux operation at aggregation will happen here. Two inputs are received and they will be combined to get the output of aggregation. And we have a serial operations of let's say this is one unit and this is one unit. There is a serial operation, as well as parallel unit is also shown here, where inputs are sent, outputs from the previous block are sent to both the blocks at a time. So they will be happening, they will be running at on their own phase. So this is our vDAG structure right now. So basically we have AI blocks. This AI blocks are given with a specialized system prompts. The system prompts are a way to control the output of a LLM. So we are using a chat interface. In our block scaling and load testing, we were using generate interface of a library. The library that we use is vLLM, and we were using a generate interface of that, where we were doing a batching operation, and generate interface of vLLM is used to get the response from the LLM. But in this case, since we wanted instructions to be given to this LLMs, so we wanted a chat interface. So in this time we have shown the chat interface. We have used chat interface of a vLLM, and we were given a specialized system prompts. And this system prompts was instructing, okay, this M1 you are just the useful assistant, where you will take a query and you will give a response to it. And for R1 and R2, we are saying, hey, you are a reviewer, just review the output of the M1 for the given input, and they will provide their output, and they will say whether it's okay, bad, good, or something like that. And then the aggregator will club both the responses of R1 and R2. Then it will try to analyze those outputs, and it will try to give the output whether it is good or not. Whichever output is good, it will pass on that output. So this is a simple vDAG we have taken in this demonstration. So before getting in detail, so we need to understand this. We have chosen these models because they are high throughput, and to understand the throughput, we have to understand the model capabilities. So like what disk size it will take, what RAM size it will take, CPU, GPU requirement, token limits, latencies, throughputs. Those things we need to have in in our hand before going for strategizing the load test. So let's take the M1, which is a phi4 mini instruct model. We were running all our experiments on FP16. We can think of running it as int8 or something like that. So parameter, this model was 3.8 billion parameters it was taking, and in the disk space it was consuming 7.2 GB, and when model is loaded, it was taking around 3.5 GB of RAM, GPU RAM. And the context size of this model is 128K, and when latencies are measured in 800 GPUs, when one instance was run in one GPU, it was taking around 1.98 to 2.89 seconds. And here, since we told like we were using batching, batch of 4 sequences were used, and the output token we asked it to generate is at the max of 256 tokens. So all our experiments are done on batch size 4 and 256 tokens only, and this was the first instance. So if I run 2 instances parallel in same GPU, and if I run the testing, right, so I was seeing then instead of 2 seconds to 3 seconds, I was seeing in 5.68 to 5.74 seconds. Both the model on an parallelly running in the same GPU, they were giving 5.68 to 5.74 seconds to generate the output. So this is on the latency side, and if I take the tokens per second token generation, so in the same 800 GPU, one instance when it was run, it was giving 89.5 to 90 tokens per second. Since we have 4 batches, so 4 batches will generate tokens at the same time, right? So that's why I need to multiply it by 4, and when you multiply it by 4, you will get a 358 to 276 tokens. So here 2 instances are there. So instead of 1 instance, it is 1 into 4. It is missing here. So when I run a 2 instances, my tokens per second was reducing because the GPU sharing is happening, right? So both the models will be fighting for the GPU's compute. So I was getting 44.97 to 46.04 tokens per second. So for a batch of 4, so when I multiply 2 instance into 4, that I will get as a 359 to 368 tokens per second. And similarly for a let's go for a Meta Llama 3.2 model that was consuming like 3 GB of RAM, 4.7 GB in a disk space, and 1.23 billion parameters was there in that model. And latency and tokens are very important for us right now. For one instance, it was taking 1.25 to 1.27 seconds, again similar to tokens and batch size of 4, whereas 2 instances were taking 2.17 to 2.18. So tokens is for one instance 203 to 205. If I multiply by 4, it will be like 812 to 820, and for 2 instance tokens per second reduced almost half, but overall throughput considered is 944 to 952 tokens. And next is Quen model. This we have shown you in the previous or block scaling, the mid-size model, the smaller model. In that we were showing these values to you maybe. So you their tokens per second we have measured in A100 as well as L4. The reason being is we had some L4 also, so we wanted to use those L4s for our load testing. So that's why the latency and tokens per second is calculated as well on L4, not just in A100. So in A100 it was taking 1.5 to 1.6 seconds for one instance, 2 instance 2.9 to 3 seconds, whereas on L4 it was taking 4.45 to 4.5 seconds. So tokens per second 160 to 164. If you multiply by 4, it will be 648 to 656. Whereas when 2 instances are run, 87 to 188, 87 to 88 tokens per second, not 188, 88 tokens, and that will lead to 696 to 704 tokens per second. Similarly on L4 it was 57 to 58 tokens only, so 228 to 232 tokens on total we were getting. The last model is Gemma 3 1 billion parameter model, so it was taking only 2 GB of RAM. The input context, so they say input context is 32K and output context is 8K. It can generate maximum of 8K tokens per tokens for one response. In A100 it was taking 1.5 to 1.51 1.5 to 1.51 seconds, whereas 2 instance 2.7 to 3.25 seconds, and the token generation 174 to 175. If you multiply it by 4, 698 to 702, and for 2 instances 96 to 97, and total will be 768 to 776. So you can always see a little bit jump of few tokens. That's because when the model instance were running, it will not, when one instance were running, it was not using GPUs completely, but when 2 instances were run, the GPU utility was seen to be in complete 100%. So that's why we are planning to run a 2 instance on each GPU in A100. Whereas for L4 I have calculated only for one instance, because when one instance was run, right, it was almost like 80 95 80 to 95 usage was happening, so there was no use of running one more instance. So total latency estimation for a vDAG. So we'll do a theoretical estimation right now based on whatever the data we have from the above data, right? So with that we'll try to estimate what will be the theoretical latency for a vDAG given an input, at what time the output might come. So for a 256 token, this all test is done on 256 token. So input block we have shown like it will take 5.68 to 5.74, whereas the R1 block it will be like 2.17 to 2.18, whereas R2 block, in the R2 block we have A100 and L4. If A100 is considered, it will give us 2.9 to 3 seconds, whereas L4 block it will give 4.45 to 4.5 seconds, and the aggregate block 2.7 to 3 seconds. So when to estimate the total, so I need to consider the input block and max of R1 R2, because whomsoever delaying right in this R1 R2, so because of that output also will be get delayed. So I have to consider the max operation of R1 and R2 and aggregate. So if I do that, I was getting somewhere around 11.28 to 11.94 if E100 is considered, whereas if L4 is considered, it will be somewhere around 12 seconds to 13.4 seconds. So basically I can say if one input is given, I would get output around 11.28 to 13.44 seconds. So this is what our theoretical estimation of latency. So you need to have an understanding of library as well. We have vLLM, batching is possible, splitting of model is also possible with tensor parallelism. So those things are possible. Right now I'll not be using model splitting because my models are very small and it will consume just like 8 to 10 GBs only. So it will easily fit in one GPU that we have, either L4 or A100. So load testing scenarios, let's discuss now. So estimate the max request per second that can be handled by each block for a given token generation per request. So we need to estimate this, then only we can start load testing. So for that you need to have a request per second from each individual block that we have, and also you need to have an idea on what all hardwares you have. So let's say M1, I am putting on a node which has a 4 A100s, because I saw that M1 was taking more times, right? So it was generating a lesser tokens. So just to show, it was giving some 300 to 400, maybe 360 to 370 tokens, whereas rest all were giving like 900, 600, 700. So that's why I was planning to give a 4 A100s for this this model, M1 model. So if since 4 instances and 4 GPUs and 2 instances, I need to multiply basically 4 GPUs, 2 instances, and 4 batch into 44.97 to 46. That will gives me somewhere around of 1400 to 1473 tokens per second. So if I divide these numbers by 256, that is around somewhere around 5.6 to 5.7 requests per second. So this way I have calculated for M1. Similarly, I need to calculate it for R1. So R1 is I have given 2 A100s only, and it is giving me somewhere around 7.3 to 7.4. And for a reviewer R2 block, so I have two instances of one A100 is available, and in that I can run 2 instances. So I was getting somewhere around 2.7 to 2.75 requests. And similarly, I'll be running 1 instances on 4 L4s. I have one node which has 4 L4s. So for them, the request per second is somewhere around 3.5 to 3.6. So when you sum it, so I will get somewhere around 6.28 to 6.38 requests per second. And for aggregator block, it was somewhere around 6 to 6.0 to 625. So now we need to get the common request per second from all the blocks, because let's say the M1 is having 5.6 and this is having 7.3, 6.2, 6.6. You cannot bombard with 10. So because you giving the 10 requests, all the blocks will be getting delayed only. So I have to use some common or the minimum available in this. So that was this block, M1 block. So 5.6 to 5.75. So since it is a floating point number, I'll take a 5 requests per second. So with 5 requests per second, I'll be doing my benchmark testing. So similarly, in our block scale testing, we were using 15 requests per second for a Quen model, Quen 1.7B model. So here we'll be using a 5 requests per second. So let's say now this 5 requests per second I am hitting, and I have 4 models. So totally it will become 5 into 4, 20 requests per second. At the end, we will get an aggregate request per second, because we have 4 different models. So so now every request is a new session ID. This is very important. So since the questions that I'm asking, right, it's not a continuous chat kind of a question, but I'll be asking different questions, because I have to randomize my question generation as well. So I was using a very randomized questions, so there was no need of a context passing at all from the one question to the second question. So for that reason, I'm using I'm creating a new session ID for each and every request, and random questions is chosen from the available corpus. We'll preload those questions available with us. We'll use some LLMs to generate some random questions. And since we have a fixed number of requests will be sent, we will not be testing the auto scaling capabilities, because I'll be setting a constant number of requests per second only all the time. So I have disabled the auto scaling so that all the scales are available at the point at T1 itself. So we'll be creating all the instances for the required for the load testing at the beginning itself. So we'll not be doing any downscale or upscale this time. So next, concurrency. So we need to understand concurrency or a in-flight request estimate. So for 256 tokens request, estimated latency is around somewhere around 11.28 to 13.44. That's what we have got here. 11.28 to 13.44. So if we want to send a 5 requests per second and our then the concurrency of our in-flight request will be, we need to multiply this request, the number of requests, into the time, the latency expected. So somewhere around 56 to 67 requests can be available any given point of time as an in-flight request. So they will be under process, they will not be processed, under process. So we have to see this kind of a number in our in-flight request. So each block should be able to handle this concurrency or in-flight request. So now let's calculate total instances or resources used in the load test. For M1 block, 2 instances on 4 A100s, totally 8 instances. And similarly for R1, 2 instances on 2 A100s, which is 4 instances. Reviewer block, 2 instances in 1 A100 and 1 instances in 4 L4, so totally 6 instances. And aggregator block, 2 instances on 2 A100s, which is again 4 instances. So totally we were having 18 instances running in A100 and 4 instances running in L4. So this is the number of instances. So total GPUs used is A100, total 9 GPUs were used and 4 L4s were used. And for logging and monitoring our metrics, right? So logging the request response time metrics DB. So we were using a time scale DB to log our request response times and the sequence IDs or session IDs. Everything we were documenting it in timescale DB, dumping in timescale DB, so that we can use our custom visualization scripts to render the metrics, like what is the number of throughputs and all things like that. And monitor is for monitoring resource utilization or a metric of a block instance each. For that we are using Prometheus Grafana combo, so we'll be showing that to you as well. And monitor the block performance during the load testing. We have to check the latencies, error rates, queue lengths, etc. From the Grafana dashboard. So that will be discussing. So this is a prerequisite. We need to run this set so that it will generate a lot of the ENVs. So let's start with the demo. Basically, right now my load test is running. I will not be running all this, but it's for you. You can experiment that. So before running, we have some policies, right? So this policies were explained in the previous video of block testing, where you require a resource allocation policy. So resource allocation policy is basically to plan where to deploy a given model. The given model has requirements. So where to deploy those models is what will be taken care by resource allocation, which node, which GPU it has to take. So such kind of the responses this resource allocation policy will give. So user will be creating those policy. Those policy codes are available in the policy folder. You can go ahead and explore those. So here we have a resource allocator policy. Then we have a load balancer policy. So basically this, whenever a request comes, how to switch between multiple instances, how to route the instances, how to route the request properly to certain instances where load balance is taken care, meaning like you are not either skewing certain you are not giving too much of requests to certain instances, so you have to balance those. So good load balancer is codes are available here, so you can check that as well. Load balancer, weighted matrix load balancer, and how to register them, all these codes. So I have already registered, I will not be doing it now. And auto scaling, basically right now auto scaling is not required. We have disabled auto scaling for all, but auto scaling code is provided in this repo as well. So which is basically it will sense, okay, there is a demand of creating a new node, so it will try to auto scale it. So right now we'll not be using it, but you can always check the code, which is similar to previous our videos. Health check policies for monitoring the running instance. So whether running instance is healthy or not, whether it is responding to the health queries or not. If it is not responding, something would have happened. Maybe it's a node would have been gone, or maybe the block would have been gone into some error state. It is not able to load, or pod would have been removed from the gates. So something can happen. So health check policy also is available. So now we need to create the blocks in cluster with the above policies. So important note. So currently batching and muxing is handled in block code itself, meaning batching is shown in the previous video. whereas muxing was not shown. So muxing we have handled it in current video. I'll show you the code, but before that, the muxing is handled in the block code itself. But in general, the batching should be handled in block code, whereas muxing should be handled in pre-processing. So the pre-processing here is pre-processing policy rule of a vDAG. So we have in a vDAG, we have something known as pre-processing and post-processing for a given block. Let's say you are connecting a number of blocks. So every block will have pre-processing and post-processing. So in pre-processing policy, we need to add the muxing logic, but because of time constraint, we have added those muxing only in the block code itself. But we can separate those muxing from the block code and we can add it into the pre-processing rule. So why we need to do that? Because in AIOS, whenever a block is created, this block can be used for a ad hoc inference, as well as we can add that to a vDAG. So if I add the muxing in the block code, I'll not be able to use that in the ad hoc inference. The reason being is, let's say a mux here mux size is 2, meaning 2 inputs are expected. When you are giving an ad hoc inference, you'll be giving one request, so it cannot do a muxing properly. So it will not be doing an inference because it is expecting one more same session ID's content. So 2 inputs are required, so that of a same session ID, so that it can mux it and then it will send it to the inference. So that's why we have to avoid the muxing in the block code. We can add that muxing in the pre-processing code, but because of time constraint, we have added muxing and batching in the block code itself. So I'll just show you the what part of the code has been changed for the muxing in our model code. So yeah, let me show you the muxer.py and the main origin.py. So yeah, this is the main file which will be running for a vLLM, and it's a vLLM batch. So here we are importing muxer.py, and so we are creating a muxer object first. I'll just show you that in the init side. Yes, a muxer object is created, and we need to pass on the mux size. So mux size settings that we have to pass in the init settings. Mux size we need to pass, and also a batch size. This we have already discussed how to do a batching and all. A batcher class is initialized here, and similarly a muxer class is initialized. And let's say a mux of 2 is sent here, so then this class will be initialized, and this muxer object we need to send in one function. So basically AIOS instance will be checking whether it has this function get muxer. If this function is available, it has to return the muxer. So user have to create the how the muxing is required. So it's a user defined function it will become. So that's why we have put it into the user side. Similar to batching and muxing are in the hand of user. So how you define a muxer is very important. So AIOS will not do that. It will simply take the give it the packets to the muxer. If muxer returns the packet, it will return to a model. So muxer class is defined here. So we are going to return the n, which is an integer number, and a process packet function will be called. A process packet function has to be there in the muxer class, and we are sending a packet. It is an AIOS packet. So if n is 1, meaning its muxing is 1, so we will be immediately returning the packet without doing anything, because there's only one input is received. So by default n is 1 only when the object is getting initialized, the muxer object is getting initialized. And we have some state variables, and the key here we are using is the packets session ID and packet sequence number are used as a key. So that combination becomes the key, and in that we are keeping a self variables and a count. So whenever the count of that variable is self n, which is like 2, let's say 2 is the input, so then only we are sending the proper merged packet. If not, we are sending a none. So if you are sending a return equal to none, AIOS understands that okay, the since it's a mux, the content is not available at ready. So I'll move on. So it will move on to the next input it has in the queue, and it will again give it to the this function. Whether again, if it is a, let's say if it is the same session ID and same sequence number, then the count will become 2, and when it is 2, then it will take the merged packet. And how to merge the packet is what it is defining here. Right now it is creating a dictionary where input is there, and it is creating an array. So you can define your structure that you want. Right now I'm taking it as an array, merging two packets, and just merging the creating it as an array of 2 items, and I'm doing a I'm sending that as an output as a base packet. So that only will be that is what a merge packet is, that's what is sent. So this JSON dumps is also very important here. So if you miss, we'll get into some errors. So this merge packet is sent back to AIOS, and AIOS instance will if it is not none, right, then AIOS instance will call the preprocess and on data functions. On preprocess is the function that is called when it has the data, and batching is also has to be done, because uh, we have a batcher, right? So once batching is sufficient number of muxed items are there, then batch is complete. Once batch is complete, then only it will go for an inference. So we have changed certain codes here for handling the chat interface as well, which I'll not explain here. So that's what the muxing and batching part of the code is, and you need to build the Docker, you need to push the Docker to the registry, and we need to register the component, because we have added some variables like init settings, the mux size and all. So that needs to be sent as a we have updated that in component and JSON registration. So you just have to register it, and then for unregistration also we have provided how to unregister and all. So now this is about the model. So let us create the blocks first, because before creating the vDAG, the blocks has to be available and up and running. So we have to create the blocks. So as we mentioned earlier, to create the blocks, first we'll create the first instance of a block. So I have a bash file here. So in the blocks folder, I have a bash file, which is a first instance. What it does is simply calls the 4 more bash files, one for each model. So those blocks will create their instance. So one instance it will create. And also very importantly, like I was saying, we have disabled the auto scaling. So I'll just want to show you that. Policy rule spec. The last one was a autoscaler. So right now I'm using an autoscaler 2.0, which is like not an autoscaling, true autoscaling. It is a dummy autoscaler, so it will not do any autoscaling. But load balancer and all, I have used a proper load balancer only. So there is no compromise on a load balancer. And also resource allocator policy is also not used properly, because we are pre-allocating. We are only determining where the each instance has to run and which GPU. So resource allocator also will not be doing much activity. Only the load balancer will be the guy which will be doing a proper tasks, and also a health check, stability check. So yeah, so the once manual allocate first block is instance is created, it will create the one instance each. Then we have to scale them, and in this bash file I have defined where it has to scale. Let me just show you that. So we have to use an API provided by the AIOS, where you can scale individual instances. So this is the API scale. This is the API where you need to provide the which cluster you want to do the call, because we are going to the gateway URL, right? So to gateway URL, we have to say which cluster we want to scale, and the operation is scaling, and this is the block ID, and total instance count required is 5. Actually, this query model is total 6 instances, 2 instances from 1A100 and 4 instances from 4L4s. So when I create the first block, right, I have seen that it will create first in A100, because A100 has a more RAM. RAM will be given a higher precedence. So the first A100 will be created. I mean, first instance will be created in A100. So that's why this node I have given again the same GPU. This node has only one GPU, 0 GPU. So again, I'm creating one more instance here. So this you need to understand. First of all, when first instance are created, you need to understand where and all it has created. So you can always check the you can log into that GPU and you can check which instance they have created. So based on that, you need to modify this. So next I have created again 4 more instances in GPU node 4, which is a L4 machine. It has 4 L4s. So only one instance I want to create. So I have given 0, 1, 0, 0, 1, 2, 3, 1, 1 GPU IDs I have given. And this is an allocation data. If allocation data key is there, right, our resource allocator will simply pass on this to AIOS. It will, if this key is not there, then only it will try to understand where it has to allocate, and also that's why we have given this key. I want to control the where it will get allocated. Similarly, for other blocks also we have done the same. For fee model, we wanted totally 8 instances because we have 4 800s is dedicated to this model. 4 800s into 2 instances, 8 instances. In that, one instance is already will be running in 0 GPU, and then other 2 instances are put in 1 1 2 2 and 3 3 third GPUs. So similarly, we have for a Llama instruct model, 3 instances are required, and as well as Gemma model, 3 instances are required. So this is the basically batch file. This will scale the instances available manually. So manual scaling is done. So now, since autoscaler is disabled, even if load is not there on those instances, it will not scale down. It will be available all the time. And to get the block metrics, right, you can always go for a this API, or you can just copy paste this URL in browser. You will get a block metrics. So this is for all the 4 blocks is available here. And we need to create an inference server. Maybe it is already created because we have shown in all our previous videos how to create an inference server. So if it is created, we don't have to create again. And now it's an important part, creating of a vDAG. How to create a vDAG is what we'll be discussing here. This was already discussed in our certain other videos, like vDAGs. So here I'm giving a name of scale test vDAG 2. This is our API for creating a the vDAG API / create vDAG, and this is actually a parser. Parser will be set up in this particular port, and this is the gateway URL, the main management cluster master. And here in the node section, I have to mention what all blocks are there. So there are basically 4 blocks, and one is a aggregate. It's a AGG aggregate block, Gemma block, and I'm giving this block ID. I don't have any pre or post process policies, so I'm keeping this empty only. But when you have, let's say, since Gemma is an aggregator, it is a mux, right? So generally we should be adding those mux kind of a policy here. We should have added it, but we are not adding it because muxing is already added in the block. And similarly, we have one reviewer, Llama 3. So this is here, this is the block ID. There is no pre-process, post-process. Similar to that, we have R2, which is when we have again the block ID here. There is no pre-process, post-process. And similarly, C4 menu, which is a input model, input, and this is the block ID here. There is no pre and post processes. And once these blocks are available, we need to create the graph. And the graph here is, first you need to mention what is the input and what is the output. Input block is M1 4 mini, and output block is this AGG Gemma. So that controller creates a graph inside their its memory, that the input has to be passed on to this. Its output has to where all it has to go, it will identify from the connection graph. So in the connection, we are seeing for R1, M1 is the input, for R2 also M1 is the input, and then for the Gemma model, which is the last output model, it has to take 2 inputs. So we have, it is wrapped inside the list. So this way a graph is constructed, and we need to run this. So once we run it, we will get a success message saying that vDAG is registered. This will not create any connections, so it will not start any, it will not be listening to inputs or anything. It is just that parser will pass it and dumps it into the DB. So once parser has dumped it into the DB, you can always run this command to check whether it has been created successfully or not in the DB. So if you run it right, so you will get the whole lot of data here. So this way you can say that okay, the vDAG that you have sent is registered. And next, once a vDAG is registered, we need to deploy a vDAG controller. The vDAG controller is basically a runtime of a vDAG. So to give an input and get the output, you require a vDAG controller that only will send the input to the first block and second block and third block and so on. So a task routing, it will handle the task routing. It will handle the health and quota monitoring rules, like whatever the policies we have, right? It will handle all those, and quality management, all those things, policies will be taken care and run by the vDAG controller. So to create the vDAG controller, we have again a API vDAG controller GCP, which cluster you want to create, action is create cluster. In the payload, you have to provide a controller new ID to it, and you need to tag it with the URI. So this URI is same as what we have created here. vDAG URI is there, right? So that URI you need to say, so that this controller will take care of running this particular vDAG. And policy execution mode local. So what this policy execution mode here is, like whenever you add a pre and post process policy where they have to execute, so that also requires some compute, right? So right now I'm saying it is local. Right now there is no policy, but what this local means is in the block code only this policy also will be run. Wherever the block pod will be running, right, in that pod only this code also will be executed. So that either you can give a local or you can give any remote executor. We have another concept known as remote executor or centralized executor. Let's say you have some nodes which is CPU only node and it has enough CPUs, so you can create a the workers in that node, and you can give that endpoint here, that in details you can provide where the central executors are. So, and replicas, I need only one replica right now. I don't want to scale this replicas. So right now we can always query the controllers with this endpoint. So let me just run this. So it is returning some responses. So I'm in this endpoint, I'm asking for a vDAG by URI. I'm giving a URI. Also, you can query it by a vDAG controller as well. So right now, since I know the vDAG URI, I'm directly querying with the vDAG URI only. But sometime what happens is controller can have multiple vDAG URIs also. So if you run this, you will how much your vDAG URIs is handled by this controller, right? So that it will display. So, but just to avoid confusion, I'm using the URI only. So here important informations are certain endpoints that you are having here. So RPC URL, REST URL, and API URL. These are important endpoints. So this RPC URL is for if you want to do inference via gRPC for the vDAG controller, you can use this endpoint. Or if you are doing a REST inference endpoint, so then you can use this endpoint. And this REST URL here is for a management command. Like say you have several policies like pre-processing policy, post-processing policies, or management policy. I mean, you have policies for a quota checker, health checker. If you want to do any management kind of activities for the management, in the sense you want to update certain parameters, or you want to do some operations on those parameters, so you have to call the REST URL, which is way for a management. So right now I need to copy this because I'm going to do a REST call only with the vDAG controller. I'll pass the input in the REST call only. So I'll have to use this API URL, and this URL you need to paste it in the YAML config YAML. So here there is a endpoint, right, inference endpoint. So this we need to paste it here, that endpoint, the IP or port, and so that our script, whenever we are running a scale load scale testing script, it will hit to the proper controller endpoint. So this way the vDAG controller is also created, and we need to run the inference. To run the inference, input structure and what happens to the input and all I have explained here. Basically, you have to give a session ID, sequence ID, and data mode. Right now we need to set it to chat, because chat interface of a vLLM is what we are going to use, because we have a system message. For that we have to use the chat interface, and we need to provide the messages. So basically the vDAG controller will send the input to the M1, because it knows the M1 is the input, and the output of M1 it will pass on to R1 and R2, and from the R1 and R2 it will aggregate, and it will not aggregate, it will send the R1 output to aggregate model, and R2 output to aggregate model. And in the load balancer of each models, right, they will be taking care of splitting the loads, and the load balancer in aggregate also will try to make sure that it will try to send the same sequence ID and session ID and sequence key will be sent to same instance. It will take care. That's how the load balancer is designed. So now to send the inference request, we need to copy that URL. This URL we need to copy, and we need to paste it here. And you can supply some prompts. So a prompt or a input you can send. So in prompt or a message, so it generate it was generate interface, but we have to use a chat interface. Instead of prompt, it has to be message, and you need to pass on certain parameters required, so that it will do a inference. But right now I will not be doing inference via here, and also it has some important parameters, retry and timeout. What that means is if vDAG fails, let's say it is trying to talk to M1, but M1 failed, it didn't if the timeout is there like 1200 seconds, if M1 doesn't respond within 1200 seconds, then it is calls as a failure, so it itself will retry to talk to M1 again. So 3 retries I'm asking it to run, and a timeout of 1200 is given here, and I'm giving a manual from session ID and sequence number. I'll not be running this, I'll just given it for a demo purpose only, but I'll be running it via some script. So this is the vDAG metrics endpoint. You need to provide the vDAG controller, and we have a global vDAG metric defined above. And when you run it, you will get this kind of a response. Currently, total retries, like what the individual means is this is the inference FPS. On an average, it's giving a 0.1 inferences per second, and latency. So on an average 9.4 it's giving. So it is for the current time only, current time, not an average or anything. So total request it has processed around 436k, and currently the in-flight requests are 53, and this is the current timestamp. Total completed is 436k, and without any retries 434k without any retries. There are 1000 odd are run with one retries. So this is basically the failures, meaning like first time it failed, and second time we did an inference, and that we got a response. So this is the vDAGs metrics. So we have added a few other metrics compared to the previous videos of block scaling, or sorry, the vDAG video. So we have added several parameters here. So it's a screenshot, just to, if in case this metric is not available. So this is the screenshot added to clean up. Like once the vDAG testing is over, you want to clean up the controller, you want to remove all those, right? So this is the endpoint for cleaning up the controller, and this is the endpoint for cleaning up the vDAG URI from the DB. And once all are removed, you can remove the blocks as well as blocks in case you don't want it. So I have an endpoint provided. I mean, I have a bash file provided. Remove all blocks. So by running this, all the blocks which are running will go from the memory, or they will be removed. And to understand, I mean, to run and visualize the response time and failure visualization, right? So we have a you can create we have already code provided, so you just have to run in a screen in the terminal. So first run this, and then you run this bash file, so that inside the screen, just make sure inside the screen it's running, so that whenever you come out of the system, you have that. It's basically a Streamlit based app. It will talk to the script whenever the script dumps, whenever it gets the request and response, right? It will dump those timestamps to 1 dB, timescale dB. So the script will read the content from there, and it will try to show some graphs. So the graphs will look something similar to this response time analysis, where this is the current run. I'll just show you for the current run. So since October 23rd it is running, and today is October 24th. So I'm just giving the session the test ID. So with that, I'm getting some data here. So this is the response time, and this is the average request per second we have sent. So on an average, we are sending 5 requests per second only, and here we are seeing some high, right? So this is a bug in the vDAG load balancer, so that we'll be working on. So as you can see here, right? So you are seeing somewhere around 8 to 9 seconds, or 8 to 10 seconds on an average. You will be seeing the response time for the complete vDAG, and this is request count over time. Till now, it has how much it has run, like 430k request it has run. And failures right now, I'll explain why the failures are 0, but failures are not 0. It will be having some numbers, and so those graphs are shown here. It's really like it was the time like around 350k a request has been processed around this time, and this is the grid, like a response grid. If you want to see certain other outputs of like some timestamps or something like that, if you want to share it, you can see it from here. And we have a Grafana dashboard as well. For Grafana dashboard, we have provided some sample dashboards in our so you can go to blocks. So there are sample dashboards. One is for a block and one is for a vDAG. So with that, I have created a dashboard like with the sample, right? I have created a dashboard here. So this dashboard is for a fee model, and I have a dashboard for a llama model as well. I have a dashboard for a pen model. I have a dashboard for a gemma model, and also I have a dashboard for a vDAG itself. So in the vDAG you will see in-flight requests. So how many in-flight requests are there? So one thing I can match is wherever in-flight requests are heavy, at that time this higher timestamp is the higher response time was seen, and this average response time is an aggregation of 60 seconds. So within 60 seconds, whatever data it has, right, it will try to aggregate and project. So it is not exactly 1000 or something, it is like somewhere around 450, 500 or so. So this is the in-flight request. So you can see on an average 48 to 49, 50, something like that. You can see on an average in-flight request, and latency in second, 10 seconds or something like that, 8 to 10 seconds, 11 seconds. And this is the total number of requests processed. This is a request per second. So this is the dashboard for a vDAG controller, and this is our dashboard for a model. This dashboards we have already explained, but we have added some more fields from the previous videos. So we have added like request process per second, some of the all instance, like we have whatever the instance are there, we are summing their request process, how much of request process. So on an average, like it looks like somewhere around 4 to 5, 5 to 5.15 request process is happening from the each model that you can see here. 5 requests per second. So this is also 5 requests per second. So it's also processing on average 5 requests per second. Similarly, you have a total request process so far, and load balancer latencies, queue length, how they are aggregating, like what is the average queue length. So things like that, and you have also tokens per second, and also you have a on preprocess, total process, average tokens average generation tokens. This is tokens per second. It is not a generation, it is a tokens per second, but this is an average tokens generated by the LLM for a given queries. So this LLM is generating around 40 to 45, I can say, on an average tokens, whereas the second Meta Llama, it might be generating again 47 to 50, though we are asking for a 256, but it might be generating 47 to 50 tokens per second. We have seen when we were having a DeepSeek kind of a model, which was again a DeepSeek Quen based model. Base was a Quen 1.5b, which is a small model as well. So the throughputs were also pretty good, but thing was it was always generating 250, 255 to 250, because it was a reasoning model, that it might generate a 250 to 55 odd tokens it might generate. So as it is a reasoning model. So this is for a Quen Unsloth Quen model. So it is also generating on an average 70 tokens per second, whereas the last model, the Gemma model, it is also generating an 65 to 70 tokens per second on an average. So these are the dashboards. So how to create the dashboard is given here. So basically you need to import the first you need to, when you have a Grafana deployed in your cluster, you need to say Prometheus as a data source, and you need to give this endpoint as a data source for that. And then you need to you can add those connection data sources, and then in the dashboard you have to go to dashboard section of Grafana. There you have to import the JSON files we have provided. So it's for a block. So since 4 blocks are there, you can copy those 4 blocks, and before that you make a 4 duplicates of those files, and just don't forget to replace certain names. Like I'll just show you that. So yeah, just don't forget to change this title, and this title is what will be visible over here. And you have to give some UID also, like randomly generate some strings. And importantly, you need to change the model names here. Request processed, data source. When you open this as a text file, you will have those details, what block ID and all. So yeah, basically the block ID here, right? So you need to replace the block ID here. So you can open it in editor, and you can mass replace this with your block ID, and then you create a 4 copies of 4 different blocks, and then you import those JSON files here. So that's what for either. So that's for blocks, and this is for a vDAG. So we have given the vDAGs. This is the vDAG dashboard. For that as well, we have supplied the JSON file. So next is our vDAG load testing script. So we have a load vDAG load test.py. What it does is basically before running this, we need to generate some sample questions. So very short sample question. It should not be again like one page. It should not be the question itself should not be one page, because we have asked it to take lesser inputs as well as generate maximum of 256 tokens only. So in this file, this will generate some file known as question JSON file. In that, like, we have already one file with the 2.1k request questions in that available. So you can directly straight away use this JSON file. So this script will use this file, and it will randomly pick the questions, and it will make sure that whatever the request per second you have asked, right? So here request RPS 5 requests per second we have asked. So it will try to make sure that it will generate 5 requests per second, and it will try to hit to the vDAG controller. This is the vDAG controller endpoint, and we are sending a vDAG param timeout, like it's for a 1000 as a timeout we have given. So vDAG controller takes this, and vDAG controller will try to do responses from each block. If it is not received within 1000, again it will try to retry. So the retry right now we have given 1, but there is a bug, so it has taken 1 retries. So that will be resolving in next release. Request time. So this is basically for the client side. So if response is not received within 1100 seconds, then we will call it as a failure. So what we observed is the response time whenever you are seeing here, right? So it was because of one bug in the load balancer that will be really, giving a patch. So because of for some very small short duration of time, like 1 or 2 minutes, so the requests were taking more than 1000. So but it was in 1000 to 1010 seconds. So because of that so because we have 1100 seconds, but the response came within 1007 to 1010 seconds, so that is not considered as a failure. So that's why the graph was showing you failure as a 0. But we will when you query the vDAG controller, right, so you will get these numbers. So this number somewhere around 1148. So this was the number that we got for a one retry. So one retry is basically actually a failure for us, first time failure. So we are restricting certain things, meaning like the maximum of 5000 concurrent requests can be sent by the customer. Let's say if because of one model there is a let's say I have, instead of this fast model, I use one model which is doing slow operations, meaning it is maintaining some queue length here, right? So you are seeing queue length 1 to 2 only is the maximum. Let's say there is an constant of 200 or 300 or 500 queue lengths. Because of this, what happens? Requests will be in-flight requests will be more, and because of that I'm just restricting. So at any given point of time there should not be any 5000 concurrency. So 5000 questions only can be there, requests only can be there. More than that it should not be there. That kind of a the boundary I have set. So the my script will never give any request which is beyond 5000. So this is the conf.yaml, and this is the DMA endpoint where we have to this is again one service. Instead of our DMA endpoint, you can always use some other service. Let's say this DMA endpoint, whenever I hit the data structure will be given in the later section. So that data will be dumped into the timescale DB, which is available running behind this endpoint. So yes. Yeah, so now to run the load test script, so you need to run the prerequisites requirement.txt, and this for Streamlit running. So requirement streamlit.txt, and also you can set up env variables by setup timescale env.sh. So you can pass on your credentials required. So I'll not be showing it here. So basically it will set up certain parameters. Right now maybe I can show it. Yes, so those again takes from the env variables only. So yeah, I don't have to worry about. So basically those variables are set, and that variables are used by the scripts, and you can run a load test. Better you run it in a screen, because this test will be running for hours together. So by running in screen, you can always come out of the screen and always you can get into the screen to check the current running progress. We have also a log file also will be available. You can always check the log file. The log file name will be load test.log. You can always tail the log file, what's going on, whether you're getting a response or not, what is the test ID. So all the things you can always log the tail the log file. And this is the structure of the data that we are dumping into a timescale DB. So where right now the block ID and user ID is dummy, because in our previous example of block scaling, we were using block ID and user ID. There we were giving proper important data, important the block ID details and user ID was given. But here there is no block ID and user ID concept. So I'm giving a dummy string, and I'm giving a request response times here in OBJ format, as well as the time epoch format. So basically the script divides the user request with the equidistant time interval based on the request rate configured in the config.yaml, that is 5 requests per second, which means 200 milliseconds one request will go from the this script. And after running the script, so after seeing all these results, right, so what is our conclusion? AI scale is performing theoretical efficiency. Whatever the theoretically you have calculated, it is, we are achieving that. So just to give some examples, so latency perspective, so theoretically we estimated around 11 to 13 seconds is what our theoretical estimation, but we are seeing around 8 to 11 seconds from the response time analysis. So except the peak timing, this peak timing is because of the bug. So apart from that, we are getting an 8 to 11 seconds. And request perspective, so we were practically we were calculating like 5.6 to 5.7 requests, but we restricted ourselves to 5 requests. So this 5 requests is properly able to handle by the vDAG controller. So vDAG controller is not lagging or anything. None of the blocks are also lagging. So theoretical to practical is almost it's same. So I mean the practically whatever number we have set, right, so it is not leading to any issues. So that's also taken care. So next is in-flight request. So we were estimating in-flight request of 56 to 67 requests because of this timings into consideration, where we just multiplied this number by 5, that is an input request per second. But on an average, we are seeing 48 to 51 requests in flight, so which is also a good sign. So we are near to the theoretical estimation. So only during this time, so this time only the in-flight requests are more. That is because a bug in the load balancer. Next, failure percentage. So to calculate failure percentage, the total failed items are 1148, whereas the total requests sent was somewhere around 3.11k. This is not recent one. This is during the time of this Python creation. So failure rate is almost less than 1%, which is 0.36%. So which is good. And the next steps, yes, we need to handle on bug in the load balancer, which fails in the mux block at certain interval of time. So, and also integrate automated quality checks. Right now, I'm not worried about the quality. The reason being is my interest was how the scaling works, though I was not interested in what is the response I get, what is the request I have sent. So such kind of things also we can integrate. We have a quality store policy, and in that store policy we can store the request and responses, and then we can assess those whether it has worked well or not with some other custom scripts. So that's it. So we have basically in this video tutorial we try to explain how to create a vDAG, and how to deploy blocks, how to create multiple blocks, and how the combination of blocks needs to be done while creating the vDAG and vDAG controller creations. And we tried showing certain APIs of vDAG controllers, and we tried showing you the response time analysis from our side for each block, and as well as we try to show you the dashboard of each and every block, how they behave, what are their responses, metrics and all. And also we tried showing you the scale test metrics, and at the end we tried to conclude our theoretical estimations and the practical output that we got. So with this, maybe we can if you have an idea of combining multiple blocks to form a complex use case, so you can always use the vDAG concept from the AIOS. So after handling the bug, we try to rerun the test again. So this bug was at load balancer, and it was having a small issues at wherever there is a mux block. And once that bug was handled, we ran the test again for a couple of days. And let me just show you the result for the recent run. So we ran this test from 24th of October to 27th of October, almost 2 days to 2.5 days, and this was the test ID, and I'm averaging it over 60-second window. So let us wait for the response to come from the Streamlit app. Yes, so this is the average response time. So on an average, you can see, right, so the number of the time it takes for a complete response to come from the load by vDAG is around somewhere around 8 to 10 seconds, and there is no spike or anything anywhere. So earlier in the video, you have seen some spikes here and there because of the failures happening at the mux. And right, I mean, this was the input given. On an average, 5 requests per second was sent throughout, and 300 is for a minute, 300 requests were sent. And this is the request count over time, around somewhere around 1.59 requests were sent until 9:30 a.m. on 27th, 9:48 a.m. And then failed requests. So there is no failed request at all. So it's completely zero. So this is about the Streamlit apps response. So I just want to show you the dashboard in our Grafana as well. So in-flight requests where stays at 48 to 50 requests. So if you divide this 48 to 50 requests by input given, so which is 50 divided by 5, which is around somewhere around 8 and 10. So we should get a 10-second latency on an average. So that's what we are getting here, 8 to 10 seconds on an average latency. And this is the blocks, each and every blocks queue length. So if you see, right, at any given point of time, there is no queue buildup happening in any of the model. So here it is it's just 1.5, less than 1 to queue lengths. And this for the model llama model, which is also having very less queue lengths. So here is one other model, the Gemma model, which is aggregator block, and it's also having very less queues, like the max. Max it has reached only 4 to 6, not beyond that at any given point of time. So this was another Quen model. So it was maximum of 2 or 3 or 4 queue lengths. So that's it for this video. So basically, after solving the bug, we are not encountering the issue of a failed request at mux site. So that's it for the video. Thank you. Thanks for watching and keep supporting.